For number 14, notice that there's a less than or equal to. That tells us we're dealing with a polynomial inequality, and our two critical values are 3 and -4. So let's plot those 2 points on a number line, and then we need to determine the regions of our solution set. 0 is a handy number in the center to substitute in. On the left, I'll choose -5, and on the right, I will choose 4. When I substitute -5 in, both parentheses become negative, and so negative times negative is positive, and we want it to be less than 0, so that number will not work. When I substitute 0 in, the first parentheses is -3, second parentheses is +4. That gives me a product of -12, which is less than 0, so values in the center will work. A value such as 4 will give me 4 minus 3, 1 times 8, which is positive, and that value doesn't work. So we only have values between -4 and 3, inclusive of the endpoints, because this inequality contains an equal sign. So our solution interval is from -4 to 3, and it's a closed interval including both endpoints. For this next problem, our critical values are 2, -1, and 5. This is an inequality, so I'm going to have to find the regions where we have our solutions. And putting these on a number line, we've got -1, 2, and 5 arranged in order. Values that I'm going to choose as test values will be -2, 0, 3, and 6. And let's see what's going to happen. No matter what number gets plugged into this first parentheses, the result is going to end up being positive because we've got a quantity squared. So I really only have to analyze the next two. When I stick -2 in the first parentheses, I get a negative. The next one, a negative, and their product is positive, and we want this to be greater than 0, so -2, ding ding ding, works. Let's try 0. First parentheses is positive, second one's negative. Positive times negative is negative, but we want this to be greater than 0. No, that won't work. Let's try 3. 3 minus 1 is 2. 3 minus 5 is -2. Positive times negative, that doesn't work either. Let's try 6. 6 plus 1 is 7. 6 minus 5 is 1. Both of these are positive. The product of positives is positive, and that's greater than 0, and that's what we want here. Because equality is not included within inequality, we're not going to include the endpoints in our interval, and our solution regions will be from -infinity up to -1, which we don't include, united with 5, which we don't include, on up to infinity. Finally, on this last problem, we have 0 on the right. Our two critical values are -5 and +3, so let's put them on a number line and then try some test values. On the far left, I'll choose -6. In the center, I'll choose 0. And on the right, I'll choose 4. When I substitute -6 in, both the numerator and the denominator are negative. We get -1 over -9. And the quotient of negatives is positive, which is greater than 0. And so, yes, -6 does work in the inequality. When I substitute 0 in, I get 5 over -3, which is negative, which is not greater than or equal to 0, so 0 does not work. And 4, when plugged in, will give me 9 over 1, which is positive, and be part of our solution set. Now, we've got two regions where our answer or solution set resides, and an equal to in our inequality, which would mean including both of our key critical values. However, 3 is not part of the domain, and we cannot include the 3 itself. So our solution set will be from -infinity to -5, which we include, and then from 3, which we do not include, on up to +infinity.